Partial differential equations. So quite obviously, it's not just in the case of ordinary differential equation, we had y as just a total y has total dependence on x. We have only one independent variable, one dependent variable, one dv, one iv independent variable on, in which case whatever changes in x, it will totally reflect in y, okay, or whatever changes in y are just because of changes in x only. But in the case of partial dependencies, suppose if I have z as a function of x's and y's, z as a function of x's and y's, I have two independent variables and one dependent variable. The value of the dependent variable completely depends upon the value of x or changes in x, also on changes in y also. Of course, it also depends upon how you define f also. It's a different story altogether. Okay, but whenever x changes, z changes. Whenever y changes, then also z changes. And sometimes there is a possibility that x also changes, y also changes. X also changes, y also changes. Then there will be some total change in z also, which would be dz. If you remember, whenever you have total dependencies, total changes that I am talking about, or total gradients that I am talking about, we always write it as dy by dx's, which represents the change in y for a corresponding change of dx in x. Similarly, whenever x changes, z changes here, and that we also represent it as dou z by dou x, because dou I write whenever I have partial dependencies. So here z partially depends on x, z also partially depends on y. So whenever x changes, z changes, whenever y changes, also then z changes. In such case, the changes in z for a corresponding change of dou y in y. The point is, dx is also infinitesimally very small change in x. Dou x also is infinitesimally very small change in x on. Just symbolic notation that we follow. Dou and d is just based on a symbolic notation based on the dependencies, number of independent variables that we have. That's it. Okay. One independent variable, we always write it as d's. Multiple independent variables, we always gradients write in terms of dous. But whatever it might be, since x is changing, y is changing, both of them can change together also, then there will be cumulatively final change in z. What is that z? Change in z. dz is always equal to dou z by dou x dx plus dou z by dou y dy. Suppose I have more than two independent variables, then I extend this one plus 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 plus. And this is what is called total change. And also there is one symbolic notation here. This small p, we write it as dou z by dou x. Dou z by dou x, we always represent it as small p universally. Universally, small p, we represent it as dou z by dou x. The same small p in the case of ODE, we were representing it as dy by dx in ODE part. But in the case of PDE, we represent it as dou z by dou x. And small q will be dou z by dou y. This is of first order. We call it this as first order derivatives. Since I have only two independent variables, in the first order, we will have two gradients. Dou z by dou x with respect to x, dou z by dou y, which is with respect to y. Gradients with respect to x and gradients with respect to y. Suppose I have more than two, I'll get some more gradients also. Now, when we go for higher order, what we'll have is dou square z by dou x square can be there along x, dou square z by dou x square, or you can even have dou square z by dou x dou y also you can have, or you can even have dou square z by dou y dou x also can be there. Finally, dou square z by dou y square also can be there. Dou square z by dou y square in the second order, higher order. Okay. These are represented as R, S and T's. So PQ, RST. PQ first orders, RST second orders. And for all our practical purposes wherein whenever these functions, z as a function of x comma, they are all continuous functions and having continuous first partial derivatives, then dou square z by dou x dou y will be equal to dou square z by dou y dou x. This is not always true. Not always true. Okay. This is true whenever z is a function of x comma y is a continuous function and also has first order partial derivatives which are continuous ones. First order partial derivatives will have two first order partial derivatives. Dou f by dou x is first order, that means P. Dou z by, dou f by dou y or dou z by dou y, which is Q. Both of them are first order derivatives. They are also continuous functions. Then only I can go for higher orders, right? In all such cases, you have dou square z by dou x dou y equal to dou square z by dou y dou x. Okay. This means that order of differentiation does not matter. Order of differentiation. What is order of differentiation? See, dou square z by dou x dou y means this is actually dou by dou x operating on dou z by dou y. That means first partial differentiation with respect to y and then partial differentiation with respect to x. That is order, the order of differentiation. First partial differentiation with respect to y and second partial differentiation with respect to x is the order here. But when it comes to the other one, dou square z by dou y dou x, it is dou by dou y operating on dou z by dou x, which means first partial derivative with respect to x and the second partial derivative with respect to y. So order has changed. You cannot, as you like, you cannot change the order. Whenever there is a change in order, the meaning also sometimes changes. Even in the case of multiple integrals also. Multiple integrals, I don't know how many of you know these multiple integrals, dx, dy. First integration with respect to x and then integration with respect to y. Sometimes first integration with respect to y and then integration with respect to x. Lot of difference in what it is, the meaning of that. The meanings would change with orders. Order of differentiation or order of integrations, meanings would change. Are you getting that? So don't apply the way you like. Whenever you have to change the order, there is a way you have to change the order. The meaning should not change when you change the order. Are you getting that? So there is a way to do that. How to do that in terms of integrals, we will see it later. When it comes to multiple integrals in different topics like vector calculus, we have multiple integrals. Integral calculus, we have multiple integrals. Or real analysis, we have multiple integrals. Wherein we will discuss what happens when the order of integration is changed. Sometimes a question can be directly asked. Solve the integral or evaluate the integral. He will give some order. Integral with respect to x, integral with respect to f of x comma y dx dy. By changing the order. Not many people get confused. What is the changing order and then integration? Because we know order of the differential equation, we know. But what is the order of the integration? Order of the integration is all about this. First integration with respect to x and then with respect to y, or with respect to y first and then with respect to x. So but finally, when it comes to integral, there is a meaning for integral, which is the infinite summation. The meaning should not change. You cannot change the integral by itself by just changing the order. So we have to evaluate in such a way that the meaning do not change by changing the order. That's how you have to do. Okay? That all those things we'll see later. But as of now, just keep note of these symbolic notation. The symbolic notation PQRST. PQRST. Small PQRST is dou z by dou x, dou z by dou y, dou square z by dou x square and dou square z by dou x dou y, or dou square z by dou y dou x is S, and small t is dou square y by, so dou square z by dou y square. Is that clear? And in the examination, not necessary that they have to give in terms of dose. They can even give in terms of PQRSTs also. Given a differential equation which has got the second order up to here, they can always use PQRSTs always. Sometimes they mention what is the notations they used. Sometimes even they don't mention also, you have to understand that this is what the notation all about, because this is universally acceptable notations. Take any textbook, Indian author or foreign author, they will be using only these symbolic notation. Is that okay? Syllabus, go to syllabus. First of all, this is part of paper 2, section B. Marks that you can expect, 60 to 70 marks. Depends. That depends on the paper setting pattern. Paper setting pattern. Okay. Next, syllabus. What we have? Formation. Formation of partial differential equation. The way we form ordinary differential equation, we have different ways of forming partial differential equation, in which, let me go a little bit detail. Generally, we have elimination of arbitrary constants. The same concept we have even in ODE also. Elimination of arbitrary constants. But in case of partial differential equations, we have extended concept which is all about elimination of arbitrary functions. Arbitrary functions. So, and what are these arbitrary functions? This is arbitrary function. Sometimes a family of partial differential equations will be given in terms of arbitrary functions, not always in terms of arbitrary constants. Sometimes it can be given in terms of arbitrary functions also. For example, I'll give one simple example. You know sphere, x square plus y square plus simple sphere is equal to r square. R is an arbitrary constant. Elimination of arbitrary constant, because I have more than one independent variable. Two independent variables, therefore obviously elimination of arbitrary constants give rise to a partial differential equation now, present case. Because earlier in OD, what did we mention? Elimination of arbitrary constants give rise to ordinary differential equation. Here elimination of arbitrary constants give rise to partial differential equation. Similarly, if I go with ellipsoid, x square by a square plus y square by b square plus z square by c square equal to 1. Ellipse, everyone knows what is ellipse, x square by a square plus y square by b square equal to 1. The extension of that in three-dimensional geometry looks like an ellipsoid. Ellipsoid. Okay. These are also called as conicoids. In fact, when I just mentioned ellipsoid, I don't know, you need to imagine certain things geometrically here. In ODE, since it is just x's and y's only, so everything is in a plane, xy plane. Everything is in xy plane. But now, in partial differential equation, since we have two independent variables and one dependent variable, dv, so we are in three-dimension geometry. So you have to start imagining in three-dimensional levels. Okay? All three, sphere, three-dimensional, ellipsoid, three-dimensional, we can have paraboloid, hyperboloids, all together we call them conicoids. Okay? And even in conicoids, we have different varieties also. We have even cone is there. Okay? And another variety is a kind of what we call cylinder. Lot many things are there. All these things we will study in geometry also, three-dimensional geometry. But certain things whenever I speak, you try to imagine in three-dimensional geometry. I keep explaining them. Okay. For example, when I talk about this, a simple thing. What is ellipse? This is A, B, B. I have major axis, minor axis. X square by A square plus Y square by B square equal to 1. If A and B are same, it becomes a circle. This is two-dimensional geometry, ellipse, a plane object, a plane figure, okay, XY plane. Now suppose I will take this area, upper half area I have taken. It looks like a plate. Upper half looks like a kind of a plate, a kind of a plate. That plate, I will rotate about x-axis for about 360 degrees. That plate, I will rotate about x-axis for 360 degrees. So this plate sweeps a volume now. It sweeps and gives me a volume. That is a three-dimensional object now. And you start imagining things. Now the imagination should go to that extent. How does that object look like? Again, that's what you need to understand. How does, when it sweeps for about 360 degrees, how does that object look like? Any object that you know? Egg? Sir, a kind of an egg. Okay. Anything else? Rugby ball, as kind of a rugby ball. Okay. To some extent, rugby ball. Okay. Like that. So that's kind of small imagination is also required. But instead, if I take this area, and rotate this about y-axis, and it sweeps another type of volume, how does that look like? Puri kind of, or kachori anta tinevatlu. Kachori, inka emanukuntavi. Bun style. అంటే మేము చిన్నప్పుడు ఫీవర్ వచ్చినప్పుడు బన్స్ తినేవాళ్ళం మేము. బన్ పాలలో నంచుకొని తినేవాళ్ళం. ఇప్పుడు ఎట్లా తింటున్నారో తెలియదు కానీ. ఓకే, బన్ స్టైల్. సో వాట్ ఎవర్, small amount of imagination is required. Small amount of imagination is required, especially when it comes to partial differential equations, because we are moving into three-dimensional geometry. Later on, even that bun also will cut into pieces, and will cut into pieces by a plane. Suppose a plane cuts it. A plane cuts in different ways also. Okay, when it cuts, how does it look like? When it looks like certain thing, and there will be a tangent plane, or sometimes normal lines would be drawn whenever the intersection happens, and all those normal lines intersect at a point, and it forms a cone. I'm trying to expand the discussion. Okay, all these things are three-dimensional imaginations. So slowly we will extend to three-dimensional geometry also. So whenever I discuss partial differential equations, I try to see that some kind of three-dimensional imagination is there. Okay, ensure that you have that. Okay, now I was discussing about arbitrary constants and arbitrary functions. Okay, when I say arbitrary constant, if you see that ellipsoid, I have A, B, C as arbitrary constants. You can easily see that A, B, C as arbitrary constants. In partial differential equations, we will have something called as arbitrary functions also. For example, x square plus y square plus z square as some function of x, y, z. X square plus y square plus z square as a function of x. The way you define the function f is arbitrary function. You can define the function the way you like. F of x, y, z equal to 0, suppose. It gives a point sphere. It gives a point sphere. If I define f of x, y, z equal to 1 constant, it gives a sphere with center at origin radius equal to 1. Or if I mention it as f of x, y, z equal to x, y, z only, it gives some other three-dimensional surface. Or if I give something else, f of x, y, z equal to x, y, z whole square plus 1, it gives some other object. Like that, all these things are surfaces, they are not curves. In three-dimensional geometry, there is no single equation which can give you the equation of a curve. Two-dimensional geometry, whatever you have drawn is a curve. Each of them has some y equal f of x equation. But in three-dimensional geometry, you cannot write a single equation to represent a curve. Not possible. Single equation cannot represent a curve in three-dimensional geometry. It always represents a surface. Example, straight line in three-dimensional geometry. What is straight line in three-dimensional geometry? Anyone who can tell me what is straight line equation? Straight line equation in three dimension. Sorry. Something like maybe x minus x naught by L equal to y minus y naught by m equal to z minus z naught by n. This is not one equation. This is not one equation actually. There is no single equation which can represent a straight line in three-dimensional geometry. Why only straight line? Any two-dimensional curve that you are thinking of, if you think in three-dimensional geometry, it is not a curve. It is not a curve. For example, you can say that x square plus y square equal to 1 is a circle where? Two dimension. What about in three dimension? Sphere. Is that sphere? Planar. Cylinder. It's a cylinder. How come this becomes a cylinder again? It's very simple. It's a circle in xy plane only. This is x plane, sorry, x axis, y axis. It's a circle in xy plane when z equal to 0. When z equal to 0, it is a circle. When z equal to 1, z equal to 0 means this one. Z equal to 1 plane would be somewhere here. Z equal to 2, z equal to 3, z equal to 4, z equal to 5. So z equal to 1 also is a circle. Z equal to 2 is a circle, Z equal to 3 circle, Z equal to 4 circle, Z equal to 5 circle. So it extends in the positive Z axis like this. And negative Z axis also it extends. So it actually forms a cylinder there. It actually forms a cylinder in three-dimensional geometry. So any two-dimension curve that you think of, when you think of it in three-dimensional geometry, it becomes a cylinder actually. Cylinder whose axis is along Z axis. Whose axis is along Z axis. We'll go deeper into this later on. Okay, fine. This is just an introduction so that you start, see, it's always like this, start opening your mind. We have a tendency, especially in maths, we have a tendency like whatever we learned in our +2 level, we always stick to that. Because in +2 level, there are lot many conditions which are there which we don't know at that point of time. I will give a simple example. Easy, work done. Remember work done? Work done? Work done by a force in moving an object along a closed loop equal to work done by a force in moving an object in a closed loop. We always have a tendency that it is equal to 0, but it may or may not be 0. It becomes 0 depending upon the nature of force. As you mentioned, if at all it is a conservative force, then the work done by a conservative force in moving an object in a closed loop is 0. In our +2 level, we always consider only conservative forces. We never ever consider non-conservative forces. And what happens if a conservative force is there? If at all conservative force is there, F dot dr becomes exact differential. Exact differential is something which we just learned on in ODE itself. Exact differential, therefore, it becomes conservative. Sometimes we also call it as irrotational force fields. A lot many other concepts which are attached to that we will discuss later. Okay. So one thing that you need to understand is not just about arbitrary constants, we have also something called as arbitrary functions. And whether it is arbitrary constants or arbitrary functions that you are thinking of, in three-dimensional geometry, all those f of x comma y comma z, they are all surfaces. They are not curves. Then how to represent a curve in three-dimensional geometry? How to represent a curve in 3D? For example, straight line is a curve. How to represent a curve? A curve in three-dimensional geometry is always intersection of two surfaces. A curve in three-dimensional geometry is always intersection of two surfaces. Straight line, suppose x minus x naught by L equal to y minus y naught by m equal to z minus z naught by n. So first two terms if I take is a plane. Second two terms if I take is a plane. These two planes intersect and gives me a line. Are you getting what I am saying? So in three-dimensional geometry, any curve that you are talking about, that curve is always intersection of two surfaces. Two surfaces always. Are you getting that? Okay. Anyway, let us continue with our discussion on syllabus. So first is obviously formation. Second is solving first order partial differential equations. Solving first order partial differential equations, in which you have two varieties again. Linear partial differential equations, non-linear partial differential equations. Linear partial equations generally is solved by using Lagrange's method. Non-linear is generally solved by using Sharp-Pitt's method. In fact, Sharp-Pitt's method also solves linear variety also. Sharp-Pitt's method is a general method wherein it can solve non-linear as well as linear, both of them. Okay. Next, partial differential equations with constant coefficients. Partial differential equations with constant coefficients. Okay. Earlier we used to have some more topics in the syllabus which are not there today. Constant coefficients. Okay. And then applications of PDE. Applications of PDE, which is really very important topic from our exam point of view. In fact, applications of PDE was introduced in 99 syllabus, 1999. Since then, till today, almost every year we have a question from this topic, applications of PDE. Earlier we used to have 300 marks papers, right? Paper 1 300, paper 2 300. In paper 2 300, I have seen one of the years there 230 markers were there in applications of PDE. 230 markers. That means just 60 marks just meant for this one. That 60 marks out of what? Then we used to 60 plus 2 12 markers, 84 marks. Earlier we used to have 84 markers for each topic. Okay. Now it is only 60 to 70 marks. So out of 84 marks, 60 marks only from one single subtopic. Imagine. So 30 marks each question. That is the length of the question. Each answer for this, each of the question, the answer would be, it goes to 3-4 pages. Very lengthy. 30 marks. Imagine 30 marks, getting 30 marks. If you don't know that, 30 marks gone. Even now also, minimum 20 marks you can expect. Suppose if it is 10 marks, they can't give it for 10 marks. Minimum 15 to minimum you will get. But generally, this question, today's scenario, 20 marks is the right one. Okay. And this also has 3 topics. One is wave equation, heat equation, and then Laplace equation. I think till 2006, I think, only wave equation used to be given. After that, slowly he started giving heat equation and then Laplace also. Okay. And then canonical forms. And then canonical forms. Canonical forms. Okay. This is our syllabus. A very simple one. Just matter of half an hour to 45 minutes. This topic. Very simple topic. This is a little lengthy one, but it's okay. This takes time actually. All these things doesn't take much time, but this takes little bit of time. This okay. These two also okay topics. Now we'll see the reference books. References. Again, the book called as ODE and PDE by M.D. Raisinghania. Or else an exclusive book on Advanced Partial Differential Equations by M.D. Raisinghania. Remember the first class that I was discussing. This book has been split into 2 parts. ODE by M.D. Raisinghania, which is now like Advanced Ordinary Differential Equations by M.D. Raisinghania, and separate PDE also is there, Advanced PDE by M.D. Raisinghania. ODE and PDE doesn't have applications of PDE, but Advanced PDE has applications of PDE covered in the syllabus, covered in the book actually. Okay, so it's up to you. Anyway, for this topic, I am going to give you a handout also. Of course, this also I'll give you a handout, but anyway, it is there in Raisinghania. I'll give anyway handout for applications of PDE. Suppose someone who already purchased ODE plus PDE together, then for them, you don't need to purchase a new book. You just take that handout is good enough. Okay. And then if you want to refer to ODE and PDE by N.M. Kapoor also, you can refer, but again I mentioned whatever the additional questions that we have in N.M. Kapoor, they are already covered in M.D. Raisinghania. Therefore, now you don't need to refer to this book. Okay. Now, there are some more books which I referred, foreign author books. One is Partial Differential Equations by Ian Snedden. Superb book. Ultimate book when it comes to concepts, extraordinarily explained. Okay. I try to see that I explain everything conceptually, properly, everything I explain in the class itself. Generally, you don't get doubts. But assuming that you have certain doubts and you want to go beyond certain limit, beyond our UPSC standard, or you want to have complete clarity of each and everything, kind of research kind of a thing, go for this book. It's up to you. Okay. But there are certain beautiful questions given in this one, which I have already covered in our class notes. So I have already picked up very, very important questions from Ian Snedden. Already picked up, and all those questions will be there in your class notes also. If you want, once the question comes, I will mention. This is from Ian Snedden, page number 56. Okay. Next. A treatise on partial differential equations. A treatise on partial differential equations by A.R. Forsyth. A.R. Forsyth. Another very good book, but conceptually okay, good book, but there are certain different variety of questions that are there in this one, again which are already picked up. I have already picked up those questions also from A.R. Forsyth, which are there anyway in your class notes again. Okay, so as far as I am concerned, as far as our exam is concerned, you don't need to refer to these books. Our exam, just because our exam requires some conceptual clarity and then solving methodologies and lot of questions for your practice. Okay, conceptual clarity anyway I will be giving in the class itself. MD Raisingane is not so good at concepts. It's good at only problems, solved examples and exercise, nothing else. Okay, so conceptual clarities you try to get in the class itself. Okay, if you are not so clear, then try to refer to Ian Sneddon. That's it, conceptual wise. But when it comes to practice, it's always MD Raisingane. There is no second book. Okay. What happens to these two guys is certain topics, subtopics, the questions from here are very good. Certain subtopics, questions from here are good. So I have picked up those questions actually. Okay, then we'll move on to concepts. Formation of PDE. Formation of PDE. First method is by elimination of arbitrary constants. Elimination of arbitrary constants. Now, look at this, just listen to me for a while, because everyone knows how to form an ordinary differential equations. Again, elimination of arbitrary constants from the family of curves gives ordinary differential equations. And the family of curves means in the case of plane curves. When it comes to here, it is all about surfaces. And you have more than one independent variable. Now, if you look at the first order, since I have two independent variables, in the first order itself, I have two derivatives. One is with respect to x, one is with respect to y. Also, I have a derivative just in first order only. Suppose if I think of reverse process, if I have to solve a differential equation, I have to integrate the differential equation. With respect to x, I have to integrate. With respect to y also, I have to integrate. If I go with a small differential equation like this, plus equal to 0. It's a first order differential equation. In order to form this first order differential equation, the given surfaces, family of surfaces, I have to differentiate with respect to x once, I have to differentiate with respect to y once, and then eliminate. There will be two arbitrary constants in the family of surfaces, which I eliminate, I will get this differential equation. Is it or not? Or else, if you don't understand this, we will think in a reverse way. Suppose this is the differential equation. In order to get the family of surfaces, what I will do? I will first integrate with respect to x, I will get one arbitrary constant. Again I have to integrate with respect to y, so that I will get second arbitrary constant. Are you getting? That means in the first order itself, the family of surfaces will have two arbitrary constants. Why two arbitrary constants? Because I have two independent variables. Are you getting? Higher order comes into picture. When you try to form the differential equation, higher order comes into picture when the arbitrary constants are more than the number of independent variables. Because there are two independent variables, two arbitrary constants. In the first order itself, I can eliminate those two arbitrary constants because I can differentiate with respect to x. I can also differentiate with respect to y. I can solve these two and get what is A, what is B. Substituting both of them in the given family of surfaces eliminates the arbitrary constants. In the first order itself, I can eliminate the arbitrary constants if I have only two arbitrary constants. But if I have three arbitrary constants, then I may need to go for higher order. So in partial differential equations, especially in the case of formation of partial differential equations, you go to higher order only in the cases wherein you have number of arbitrary constants more than the number of independent variables. Because if you have arbitrary constants exactly equal to number of independent variables, in the first order itself I can get the differential equation. Now, another question would appear here. Suppose when I go for higher order, I have three arbitrary constants. For example, plane equation, x by a plus y by b plus z by c equal to 1. Plane intersect form, or ax plus by plus cz equal to 1. Plus d equal to 0 also has only three arbitrary constants. Or x by a plus y by b plus z by c equal to 1. A, b, c, three arbitrary constants. And the number of independent variables? Independent variables, 2 only. The third one is a dependent variable. The number of independent variables are 2 and the number of arbitrary constants are 3. Therefore, we need to go for higher order. Now, when you are going for higher order, shall I go with dou square z by dou x square? Or dou square z by dou x dou y? Or dou square z by dou y dou x? Or dou square z by dou y square? There are different possibilities with respect to x, with respect to xy or yx, or with respect to y and y. You can go to any format. You might get different differential equations altogether after elimination. All those differential equations represent one family of surfaces only. Whenever you are going for higher order, there is a possibility of getting different partial differential equations. Sometimes with respect to R, sometimes with respect to S. Remember RSTs? Sometimes with respect to T, or sometimes some other combination, RSTs combinations. But still, all those differential equations, all of them are correct only. All of them actually represent the same family of surfaces. If you solve all those differential equations, finally you will land up at the same family of surfaces. So the same family of surfaces can have different differential equations. In the case of partial differential, it's because of higher order. If it is of first order, it's okay. We'll get almost the same everyone. But if it is of higher order, it may grow for different differential equations. Getting that? Okay. Take a note. In the family of surfaces, if the number of arbitrary constants are more than the number of independent variables, if the number of arbitrary constants are more than the number of independent variables, then the process of elimination of arbitrary constants, then the process of elimination of arbitrary constants leads to higher order partial differential equation. Okay. Take a question. Obtain the PDE by eliminating the arbitrary constants. Obtain the PDE by eliminating the arbitrary constants a comma b from z equal to x minus a whole square plus y minus b whole square. Z equal to x minus a whole square plus y minus b whole square. So this would be equation number 1. How many arbitrary constants? Independent variables. So it leads to first order only. So partially differentiating one with respect to x, we get dou z by dou x. Immediately you can write it as small p equal to 2 times of x minus a, equation number 2. Partially differentiating one with respect to y, we get dou z by dou y, which is equal to q, is 2 times of y minus b, equation number 3. Substituting a comma b from 2 and 3 in 1, we get z equal to p by 2 whole square plus q by 2 whole square, which is 4z equal to p square plus q square, is the required PDE of 1. Okay. Is it okay? Simple one. So everyone knows how to do that. Next one. Obtain the PDE by eliminating a comma b comma c from x square by a square plus y square by b square plus z square by c square equal to 1. X square by a square plus y square by b square plus z square by c square equal to 1. Okay? You try to do that. So how many arbitrary constants? Arbitrary constants 3. Independent variables 2. It leads to higher order. Partial differentiation with respect to x gives me this one. 2x by a square plus 2z by c square into dou z by dou x. So 2 cancelled off, and then partial differentiation with respect to y gives me y by b square plus z by c square q equal to 0, equation number 3. So going for higher orders. So partial differentiation of 2 with respect to x, suppose. I'm talking of dou square z by dou x square I am looking for. 1 by a square plus 1 by c square into z pqr plus p into dou z by dou x, p square equal to 0, equation number 4. Eliminating a and c from 2 and 4 gives so this equal to minus of that, this equal to minus of that. So cross multiplication gives me x into zr plus p square equal to pz. First answer. Hello, Chindide? Simple. This equal to minus of that. This equal to minus of that. One over the other. 1 by a square, 1 by s cancel. 1 by c square, 1 by c square cancel. Cross multiplication. That means this bracket multiplied with x, 1 multiplied with pz. Okay. This is one answer, 100% correct answer, no doubt in that, okay. But along with that, you can have multiple other partial differential equations also. For example, partially differentiating 2 with respect to y, suppose. 2, first order one, with respect to y I partially differentiate, I will get 0 plus 1 by c square into z into p partially differentiated with respect to y gives s plus p into z partially differentiated with respect to y q equal to 0, which gives me zs plus pq equal to 0, which is second answer, and this also is 100% correct answer. Nothing wrong, because you have multiple ways of getting a PD, and different partial differential equation looks to be different, but they are not different. Okay, one more way is there. Partially differentiating 3 with respect to x, so x का y. Partially differentiating 3 with respect to y gives 1 by b square plus 1 by c square into z. Q partially differentiated with respect to y. Q partially differentiated with respect to y. T plus q into z partially differentiated with respect to y. Q square equal to 0. So this is equation number 4, 5. Eliminating B and C from 3 and 5 gives. So that's a minus of that, is a minus of that. So y into zt plus q square is equal to qz. This is third answer. All the three are 100% correct. All of them, if we solve, leads to only one family, that is conicoids family. Find the differential equation of, very good question. Find the differential equation of all spheres of radius lambda and having their centers on xy plane, having their centers on xy plane. First of all, how does they look like? Sphere is center at A comma B comma C, radius equal to R, suppose R. So such a sphere looks like x minus a whole square plus y minus b whole square plus z minus c whole square equal to R square. How many arbitrary constants? దాంట్లో అడుగుతున్నా, దీంట్లో కాదు, దాంట్లో 4 ఉంటాయి. Centerలోనే there are 3 arbitrary constants. In center itself I have 3 arbitrary constants A, B and C. Along with the radius also 4 arbitrary constants, of which he has given find the differential equation of all spheres of radius lambda only. Now the radius is lambda, it's not R. Lambda is fixed now. Lambda is a fixed constant, 1, 2, 3, 4 like that. It's a fixed constant. Along with that, what else is given? Centers on xy plane. It means the center z coefficient is 0. That means C is 0 now. How many arbitrary constants? Finally, 2 arbitrary constants. Number of independent variables? 2 only. Lambda is not arbitrary constant. Lambda is a given constant, fixed constant. Okay, therefore there are only 2 arbitrary constants and 2 independent variables. Therefore, elimination of arbitrary constants leads to first order. First order. So z square into p square plus q square plus 1 equal to lambda square is the partial differential equation of the given family of spheres whose radius is exactly equal to lambda and having their centers on x, y plane. Okay. Take one more similar question. Good question. Find the differential equation of the family of spheres. Find the differential equation of family of spheres of radius lambda, with centers on the with centers on the plane x equal to y. With centers on the plane x equal to y. Then A becomes equal to B. If A and B becomes equal, C is some different. That means such spheres will be x minus a whole square plus y minus a whole square plus z minus c whole square equal to lambda square. How many arbitrary constants? 2. How many independent variables? 2. For elimination of arbitrary constants leads to first order. Get the answer. Make it fast. What answers you got, you just let me know. P square. What's P plus Q and agree. Okay. So what actually you get is partial differentiation with respect to A gives x minus x plus A plus z minus c into P equal to 0, y minus A plus z minus c into Q equal to 0. The tendency is substituting x minus A equal to minus of, y minus A equal to minus of into that one. Perfect. Which gives me z minus c whole square into P square plus Q square plus 1 equal to lambda square. But thing is, C is not yet eliminated. So to eliminate C, somewhere here you need to take x minus y, subtracting one on the other. Gives me x minus y plus z minus c into P minus Q equal to 0, which gives me z minus equal to minus of x minus y by P minus Q. Now this, if I substitute here, I will get this answer. Because elimination of that C also is important. It's not just elimination of A. You have to eliminate both the arbitrary constants, A as well as C. P plus Q enduku vachindi neeku? Avadu kada? Okay. Take one more question. Find the PDE, partial differential equation of. Find the partial differential equation of planes, PLANES, planes having equal x and y intercepts. Having equal x and y intercepts. Equation of a plane having equal x and y intercepts. First thing, intercept form of a plane, x by A plus y by B plus z by c equal to 1 is intercept form of a plane. Like intercept form of a straight line, x by A plus y by B equal to 1. For a plane it is x by A plus y by B plus z by c equal to 1. Now a question, there is one question that you should have asked here. For circle or ellipse, we mentioned for 2-dimensional curves, in 3 dimension becomes a cylinder. But what happens for a straight line? It becomes a plane. Plane also is a cylinder actually. Plane enti cylinder avtam enti. మేము ఇట్లా కట్ చేసి ఇట్లా ఓపెన్ చేస్తే cylinder plane అవుతుందేమో. Not like that. The definition of a cylinder is locus of a straight line. Locus of a straight line, a moving straight line. A straight line. Okay? Parallel to some line, which we call it generally as axis line, but whatever, parallel to some line. Locus of a straight line parallel to another line. Passing through some other curve. Passing through some curve. So, I have some curve here, some curve is there, suppose circle is there. Okay? Suppose through the center I have a line called as axis. Now my cylinder is axis of a line parallel to the axis passing through the circle. So locus of the straight line parallel to a line passing through a circle gives me a circular cylinder. Gives me a circular cylinder, right? Straight line suppose. Locus of a line, okay, parallel to some line, there is some line, so I assume some line is there like this, okay, passing through the given curve. What is the locus? Is a cylinder. It actually comes out to be a plane, right? So locus, even if I mention that two-dimensional equation of a line in 3-dimension, it again becomes a cylinder which actually is a plane actually, okay. For example, if I say ax plus by plus c equal to 0, it represents a plane in 3-dimensional geometry. It represents a plane in 3-dimensional geometry, okay. Anyway, this is intercept form of a plane where A is x-intercept, B is y-intercept, C is z-intercept, and given that both x and y intercepts are same, therefore A equal to B. So how many arbitrary constants? 2. How many independent variables? 2. Elimination of arbitrary constant leads to first order.